Good morning students, how are you? Students, in this lecture, we will study about the applications of Ampere circuital law. We will know how to determine the intensity or the strength of magnetic field due to the infinitely long straight current carrying conductor. We will know how to determine the intensity or the strength of magnetic field due to the current carrying solenoid. And we will also know to determine the magnetic field due to the current carrying toroid. Okay, so first of all, we will determine the intensity of magnetic field or the strength of magnetic field due to infinitely long straight current carrying conductor. Okay, so consider about the straight current carrying conductor like this. This is the straight current carrying conductor, and this line, dotted line, shows the axis of this current carrying conductor, and current is threading through this conductor I along this direction, upward direction. Due to this current here around this straight conductor, magnetic field will be produced, and the magnetic lines of force will be as concentric circles. Okay, so we will discuss about this straight current carrying conductor in three cases. First, what will be the strength of magnetic field outside the straight current carrying conductor? And second case, what will be the strength of magnetic field at the surface of this straight current carrying conductor? And the third case, we will discuss what is the strength of magnetic field inside this straight current carrying conductor. So first of all, we will determine what is the intensity or strength of magnetic field outside the current carrying conductor. So draw the imaginary circular loop. That imaginary circular loop is called Amperian loop. Consider about the small element of length dl at point P. Here, what will be the direction of this small element? This is not current element, only this is small element. So what will be the direction? You know, because this point, observation point P, is inside the magnetic field of this straight current carrying conductor, so any line of force can pass through this observation point, and the line of force will be circular. So the direction of small element dl at point P will be along the direction of tangent drawn from point P on this magnetic line of force or Amperian loop. Okay, so this will be the direction of dl, and the strength of magnetic field at point P will be B due to this straight current carrying conductor. And what will be the direction of this magnetic field? By the right hand thumb rule, let this blue color is the small element dl is taken on this Amperian loop. Draw a tangent at point P. So the direction of tangent at point P will be perpendicular to the direction of current flowing through the conductor like this. The direction of this tangent will show the direction of magnetic field. So this is the tangent. So the direction of magnetic field will be along the direction of tangent. Here you can see that the direction of dl and the direction of B are same. By the Ampere circuital law, the line integration of magnetic field produced at point P is equal to mu naught into I, where mu naught is the absolute permeability and I is the current threading through the conductor. This is the dot product of two vectors. So by the formula of dot product of two vectors, here vector b dot vector dl will be b dl cos theta, and it is equal mu naught I, and this theta is the angle between vector dl and vector b, but the direction of vector dl and vector b are same, that's why the angle between them will be 0 degree. On putting the value of theta in this equation, here b dl cos 0 will be equal mu naught I, but you know that the cos 0 degree is equal 1. So b dl into 1 will be mu naught I, or integration b dl will be equal mu naught I. Okay. B, for constant distance of point P, B, the strength of magnetic field will be constant. So we can take it common, then equation will be B into integration of dl will be equal mu naught I. What is the dl? dl is the length of this small element, and we know that this circular loop consists of the number of small elements, and these small elements make a complete closed Amperian loop, and this Amperian loop is circular. That's why the total length of all the small elements will be equal to the circumference of this circular loop, of this Amperian loop. That's why the value of integration dl will be 2 pi r, where r is the radius of the circular loop. Okay, and mu naught I, or b will be equal mu naught I upon 2 pi r. This is the magnitude of magnetic field at point P. If this observation point would here, so what would the intensity or magnitude of magnetic field? Because the distance of this point from this origin point or this axis is same, this distance is same, because this is the circle and these are the radius of the circle. That's why at each point on this Amperian loop the magnetic field will be same. Okay, and that will be equal b equal mu naught I upon 2 pi r. Means the magnetic field is being determined along the circular loop. This circular loop is called Amperian loop. That's why this relation is said to be the line integration of magnetic field along this circular loop. This magnetic field is not being determined along the current carrying conductor. This magnetic field is being determined along this Amperian circular loop that is perpendicular to the current carrying conductor, like this. If we have to determine the magnitude of magnetic field on the surface of straight current carrying conductor, we have determined the magnitude of magnetic field outside the straight current carrying conductor at any point is b equal mu naught I upon 2 pi r, where r is the distance of observation point. Okay, that is this. Students, if we have to determine the strength of magnetic field on the surface of the straight current carrying conductor, means the observation point will be taken on the surface of the conductor like that here. So what is the distance of this observation point? So the distance of the observation point from the axis of the conductor will be equal to the radius of this straight current carrying conductor. So we will have to draw an Amperian loop like this. This circular loop is the Amperian loop of radius small a passing through the observation point P, which point is lying on the surface of the conductor. Okay, here current is flowing through the cross-sectional area of radius a is I, means current does not change. So the magnitude of magnetic field at point P, where A is the distance of observation point from axis of this straight current carrying conductor, and the distance of observation point from the axis of the straight current carrying conductor is equal to the radius of this conductor. So this will be the magnitude of the magnetic field on the surface of the straight current carrying conductor. Now third case, if the observation point has taken inside the straight current carrying conductor like that, look at here, let this observation point is brought inside the straight current carrying conductor, let this point is this. So we have to draw the Amperian circular loop passing through this observation point, and let the radius of this small Amperian circular loop is small r. So here at point P inside the conductor we have to determine the magnitude of magnetic field will be B equal mu naught I E upon 2 pi r, where IE is the current threading through this cross-sectional area of this conductor. So this IE will be less than the current I. So what will be the value of IE? We know that the current flowing through any cross-sectional area is directly proportional to the cross-sectional area. Okay, or we can write I equal K cross-sectional area pi r square. Cross-sectional area is pi r square, where r is the radius. For IE, it will be K pi and r square, where r is the radius of this small circular loop. Total current threading through the cross-sectional area of radius small a will be equal K pi a square. Okay, let this equation is first and this equation is second. So dividing equation first by equation second, so we will get IE upon I will be equal K pi r square upon K pi a square. Pi k cancel. Here IE upon I will be r square upon a square, or so IE will be equal r square upon a square from this equation into I, where I is the total current threading through this straight current carrying conductor and IE is the current threading through this small cross-sectional area. Okay, so the intensity of magnetic field at this point will be B equal mu naught IE upon 2 pi r, where r is the radius of this circular loop. On putting the value of IE from this equation, B will be mu naught upon 2 pi r into r square upon a square into I. Okay, r cancel from r, so B will be equal mu naught I upon 2 pi a square into r. Okay, this is the magnitude of magnetic field inside the current carrying conductor. The strength of magnetic field outside the straight current carrying conductor is B equal mu naught I upon 2 pi r, where r is the distance of the observation point. The magnitude of magnetic field outside the straight current carrying conductor is B equal mu naught I upon 2 pi r. Here mu naught constant, I steady current, 2 pi constants means B inversely proportional to the R. Okay, and the magnitude of magnetic field inside the straight current carrying conductor is B equal mu naught I upon 2 pi a square into R. Here mu naught constant, I constant, 2 pi constant, a radius of the straight current carrying conductor is constant, so B directly proportional to R. Now what will be the graph between distance and the magnetic field? Let this is the distance axis R and this is the magnitude of magnetic field axis B along this direction. B is directly proportional to R means the graph between B and R will be straight line like that. Here conclusion is that the magnetic field inside the straight current carrying conductor is directly proportional to the distance. Okay. The distance of this point is R equal A. It is equal to the radius of the straight current carrying conductor. And outside the conductor, magnitude of magnetic field is inversely proportional to the distance. So the graph for B and R will be like that. So this is the graph between magnetic field and the distance. I hope you to have understood all the concepts. Okay, thanks.